Hello, and welcome to my talk on optimizing milling circuit operations using continuum-armed bandits. I'm William, and I work at a company called Mintech. We're a South African Science Council in Johannesburg. You can see our offices there in the top photo. We conduct research into minerals processing and metallurgy. We provide various services and products for both the South African and international mining industries. I work in the section that deals with advanced process control, where we develop software as well as some specialized instruments, like the two in the middle photos. My talk will start out by introducing milling circuits and how to operate them optimally. I'll then speak briefly about bandit problems. I'll discuss the agent that I developed in this work, focusing on the models that it learns and the training process. Finally, I'll show the results and some concluding remarks. So let's talk about mills. The purpose of milling is to reduce particles in size from a few centimeters or maybe tens of centimeters down to tens or hundreds of micrometers. Inside a mill, we have this ore here. These steel cylindrical structures are the mills. Now you can see inside we have this chap. He is replacing the liners. When the mill is operating, it will spin around, lifting up these particles, throwing them into the air, and they will come crashing down. That impact and the friction of all of these particles moving will slowly grind them down and break them apart. Now these liners also experience wear and tear, so they will slowly erode over time. Now how do you operate this circuit efficiently? Well, Van der Westhuizen and Powell conducted experiments at South Deep Gold Mine back in 2006, and they published their results, which we see here. They experimented by operating the mill at different speeds. We see two speeds here, 65% and 75%, and at different volumetric fillings, which are shown on the x-axis. And what they found was that by adapting these two parameters, they could change the throughput and the power consumption to reach a point where they've maximized throughput and they've minimized the amount of energy used per ton of ore processed. As you can see, these curves depend both on the speed at which the mill turns and the volumetric filling. Importantly, they were also able to relate the weight of the mill, which we can measure, to the volumetric filling, which is challenging to measure. So in this work, we focus on selecting the optimal weight and the optimal speed. Our simulation environment is built on these curves. They published in 2006. I've added a revenue model that is based on the gold price, and I've added a cost model that uses Eskom's tariff schedule with peak, off-peak, and standard rates. Now, a multi-armed bandit problem is one where you have a finite set of actions and you have to select the best action. Each action gives you a reward with some probability. We can see in this example we have 5 actions, and it's clear that action D5 will give you the best reward most of the time. So the bandit wants to find this action. Now a continuum-armed bandit extends this to the case where you have infinitely many choices. Here your actions are continuous variables, which fits our problem very well, as our actions are rotational speed and target weight. Let's talk about the agent. Your typical reinforcement learning agent will receive one reward. In this case, profit is the logical choice. But in reality, profit can be made up of one or more sources of revenue. There can be multiple sources of cost, and there are also constraints that you don't want to violate. In our case, throughput is our source of revenue. Power is our cost. We also have an overload signal. Now, if you overload the mill, you have put too much ore into it, and you risk damaging the mill, so you want to avoid that condition. Now, we model throughput and power using a polynomial model, and we model the overload signal using a support vector machine classifier. Our key insight here was that we could model each of these separately with simple models, and then combine those in a known equation that can be nonlinear or even time varying, and then apply numerical optimization. And all of this is still compatible with the Continuum-Armed Bandit algorithm for Thompson sampling, making it possible to deal with a wide range of situations. For those of you that are familiar with reinforcement learning and Q functions, or action value functions, this is the form of the Q function that we use to model our power and our throughput. It has two inputs, the speed of the mill and the target weight, and it's a quadratic function. The agent is learning the vector theta for each of the models. Our final reward is written as this function h, which combines the individual reward models. On each step of the simulation, the agent goes through these 4 steps. First, it explores using Thompson sampling, where it samples a random but likely set of model parameters. During the beginning of the simulation, we have a high degree of uncertainty about the value of the parameters, and this drives exploration. As we explore, the uncertainty is decreased. That is that covariance term. Once we have the model parameters, we act. Here, we solve a constraint optimization problem to find the next action. Our constraints are action limits that are imposed for safety reasons, and learned constraints, which are learned via our support vector machine. We then get our reward signals, power, throughput, and overload, and those go into updating the models. We use robust linear regression to update our polynomial models and to estimate the covariance of those model parameters. Let's look at the results. This shows the first 288 steps of the simulation test. This is one of the tests that I conducted. We see here that it takes the agent about 120 steps for the models to accurately learn the behavior of the mill. Once that has been achieved, the agent is able to rapidly approach the optimal operating conditions. So that happens at about this point here, where we see it rapidly increases the reward. The maximum reward is around about 420,000 Rand per 15-minute step. The full simulation covers 50,000 time steps, or 1 year and 5 months in simulation time, and it includes liner wear. Now, as the liners wear out, the target weight that is required to achieve a certain volumetric filling decreases. So the agent needs to decrease the target weight over time to keep the mill at its optimal operating point. And we see here that the agent does that. This step change here is where the liner is replaced. We see that the agent rapidly adapts to the behavior of the new liners. This step change takes about 100 steps, and that is 25 simulated hours. So in conclusion, the agent is able to adapt continuously, and importantly, it adapts faster than is typical of mill operators. I've shown it handling one constraint here, but it can handle multiple constraints using the same framework. Even under conditions of high measurement noise, it was able to achieve 98.45% of the maximum possible performance or reward. Our next step is to take this to a real-world test. We do still have one challenge, which is that it learns a bit too slowly when the mill liner is changed. Now, to accelerate this rate of adaptation, there's a trade-off between the peak reward that it can achieve and how rapidly it can adapt. So we're still working on improving that part of the agent. Thank you.